Thank you very much, Yassi. It's a pleasure to be with you all, and thank you for joining. Today I'll be talking about, I'm gonna just turn off my camera. Okay, today I will be talking about software for managing large-scale job campaigns at ALCF. I support these types of tools here at the facility in the data science group. So what we will address and what we will cover today, we will address how to deploy large computational campaigns of many jobs on our machines, and the types of workflow tools that are useful for this need. So the topics we will discuss is first, we'll be talking about these large campaigns in the context of workflows. So I'll talk a little bit about what is a workflow. Then I'll talk about how to approach workflows of varying sizes and what are workflow tools and why are they useful. Then I'll talk about how to use two tools on our machines, one called Parcel and the other called Balsam, and what they're useful for and how to run them on Polaris. And then I'll conclude by discussing how to get more information and help with your workflows. So to start off, what does a large job campaign entail, or what is a workflow? Well, large job campaigns where a user runs a large number of jobs are often discussed in the context of workflows. And a workflow is simply any collection of computational tasks run to achieve a result. Workflows can vary in size, and most users have some type of workflow, whether or not they call it that. If you just think to yourself, what are the steps I take when I log on to one of our machines, one of the machines at ALCF, what do I do in order to create a job, start it running, and get the results I need from the outputs? That's your workflow. So we'll discuss workflows in the context of the machines here at ALCF, but many of the considerations and tools I'll discuss apply to other HPC machines. So if you're a user at NERSC or ALCF or your local university cluster, some of these strategies will be useful there as well. On the right, I have just sort of a little example. This is a paper from the desk collaboration. This is a collaboration simulating sky surveys for astronomical surveys. So, they have a situation where they have to sort of create these synthetic catalogs. They have to create many images from these catalogs, and to organize and to orchestrate this workflow, they use the tool Parcel, which we will be discussing today. So first, let's talk about some common workflow patterns. So, there's many types of forms your workflow may take, and, we'll cover some tools and general strategies that can fit into different pieces of these different patterns, but it's good to just start with an overview of what we're talking about. So the first is you just have a very large collection of tasks, maybe, thousands, tens of thousands, a million, many millions of tasks. And how do you deploy that scale of tasks onto our machines? The second is you might have a little bit more complexity in this large collection of tasks. So you could imagine you have a situation where some tasks depend on the output of other tasks. So once you start having these dependencies, you have to have some method or tool for creating this coupling, for example. You might have a workflow where tasks, once they're completed, generate new tasks. So this is a common pattern we see in workflows that are using AI or machine learning models. So you might, for example, use some simulations to train a model, and then maybe use that trained model and model inference to create new simulations that you will run, for example. This is a pattern where you may not actually be able to know before the workflow runs how many tasks you will actually be running in a situation like this. So you can have these dynamic workflows. And then you might have workflows where it relies on some kind of data that comes from somewhere else. So a common pattern we see is, especially for workflows supporting experiments, you might need to, as part of your workflow tasks, stage in data from maybe a remote server, run a job on our machine here at ALCF, and then stage out some kind of data product from that analysis back to the remote machine where you pulled in the original data from. So this is also something that you would need some kind of tool to orchestrate those data transfers and to initiate the job starting on our machine once the data comes in. So we can start by just sort of talking about the first pattern, the large collection of tasks, because I think if you sort of start to think through the scale of this this example, you start to realize and think through some of the considerations that maybe apply to many types of workflow patterns. So this is often where people start. You might have just a few tasks, and there's some insight projects that their work is contained within just a few very large computations run on our machines using MPI, for example. So in this situation, let me just move this toolbar. This is sort of human scalable. Each task can be run as its own job on the scheduler that a user can set up by hand. So for example, you could write a directory, write a batch script, submit it to the scheduler, and that's that. Like, a human can type all of those commands pretty easily. So if you start to think, all right, let's go up from 1 to 20 to up to 100 tasks. At this point, human scaling starts to become uncomfortable. Like, it's not really pleasant to be doing all of these things by hand. But maybe a user could write a few bash scripts that would automate the steps that they would normally take by hand. And this could be a perfectly sufficient solution for this scale of workflow. Maybe that's all you need. Now let's consider scaling up to maybe, 100 tasks or more, 200 tasks, 300 tasks. At this point, some external factors start to, it's not just your ability or your patience that is being tested here. Queuing policies start to become an issue. So for example, on Polaris, we only allow users to have up to 100 queued jobs at one time. So if you have 200 jobs, you cannot put them all on the queue at once on Polaris. You would have to do it in 2 batches, for example, and that's inconvenient. So at this point, many people start to think about running like ensemble batch jobs. So you could run multiple tasks within one batch job on the scheduler. And there are ways to do this. They're called ensemble jobs, and there's a link to our documentation for some examples on Theta. But there's some limitations here. Like, this is a good solution if you know all of your tasks are going to take roughly the same amount of time, but ensemble jobs don't have the ability to refill idle nodes. Like, if you start, 100 tasks going at once in one batch job on 100 nodes, if 90 of them finish after 10 minutes and 10 continue for 2 hours, those 90 nodes will remain idle, but you will still be charged that time in your allocation. So it's not always an efficient use of the batch jobs. Your utilization can be poor. And so at this point, you might start be thinking about, maybe there's a better way to do this. Maybe there's a tool I could use. And of course, like, the problem only gets worse as you go to 1,000 tasks at this scale. You start thinking about, okay, I need to be packing jobs into a batch job efficiently to minimize idle nodes, but also, how do you even judge the outcome of these runs? Like, how do you judge whether they were successes? Like, if you had to look at 1,000 files or over 1,000 files, that's very difficult. And what happens if some number of tasks fail? How do you restart them? If 10% of these tasks fail, that's 100 jobs. That's a lot to handle. So at this point, a workflow tool really becomes a must because they are designed to handle all of these considerations. And just for context, to talk a little bit about the scale of our machines here at ALCF, like if you were to say, for example, you wanted to run, a task on every core on theta all at once, that's over 280,000 tasks. So that's even that's just a whole other scale. And then if you start to think about our machines that use GPUs, you might want to be running one task per GPU. That's, maybe 2,000 or so tasks on Polaris. On Aurora, that will be 60,000 concurrent processes that you could be running at once. And yeah, at that scale, you need some kind of tool. So hopefully I've convinced you a workflow tool can be useful. A workflow tool is simply just a piece of software that orchestrates the execution of a large number of tasks. It can handle running many tasks concurrently or in serial, one after the other. It can handle task dependencies. It can automate error handling and restarts. And it can also orchestrate data transfers as well if you need that. There are many tools out there, and I can't possibly cover all of them. A few tools that are commonly used here at ALCF are Balsam, Parcel, and Fireworks. I'm going to focus on Balsam and Parcel here today in the tutorial, but of course, if you need help or support on any of these tools, please reach out to us. And I will also say there's another layer of tools you might be familiar with that are often talked about in the context of workflows. And these are tools that enable hyperparameter searches or running ML inference models that often couple to workflow tools. These are tools like DeepHyper, LibEnsemble, and Colmena. And these are very interesting and useful tools. They often will couple with tools like Balsam and Parcel, which are really used to deploy work on the machine. That could be a very interesting talk, but that's not something we will cover in this talk here today. So let's start talking about some tools and how to use them on our machines. So we'll start with a tool called Parcel. This is a parallel programming library for Python. You can install it in a conda module or in a Python virtual environment using pip. Parcel works by defining apps that will run some set of computations. So this can either be simply a Python function, or if you have an external executable, you can write what's called a bash app that will wrap around that executable. These apps return what's called a future, which is a proxy for a result that may or may not yet be available. And these tasks, these futures can run concurrently, respecting any dependencies that you build into them. It's a very popular tool here at the facility. It has a community of over 70 developers. Many of them are here at ALCF and in the Chicagoland area at UChicago and UIUC, including Kyle Chard and Yadu Babuji. Here on the right, I've just sort of given an example of how you would install Parcel in a conda module on Polaris, for example. And here is some examples of just a Python app, which just looks like a Python function if you're familiar with Python. And all you need to do is import the Parcel module and add this decorator, this Python app decorator, and that will create a Parcel app. So if you have a program that's if your application is written in Python, this might be a really appealing tool. Like you might just have to put on some decorators and you will be able to then run all of your functions concurrently using Parcel. And then here is an example running the same application, Hello World, but Instead, it uses a bash app, so it runs the command line echo, and you can see how that looks a little different, but both of these apps accomplish the same thing. So I've alluded to futures and that Parcel uses futures, and indeed there is in Python something called the concurrent futures module, and that Parcel is basically just an extension of that. So it works by creating tasks that invoke apps, and the apps return an app future object. And you can build up task dependencies by passing these app futures from one task to another. So on the right here, I have sort of two examples, one where you're creating two tasks, D1 and D2, that are independent of one another. So they can run concurrently. If you have enough resources to run these tasks, like they can run at the same time. And then any subsequent, statement in your script that depends on the results returned by the future, they will wait until those results are returned. Now, suppose you want to run some dependent tasks, you can do this by simply passing the results of one app to another app. And in that way, you create a dependency, because this task will only be created S once the task D returns its result. And in that way, these tasks will run in serial. So this is just sort of some snippets of code. What does sort of a more complete example look like, and how would you run it on one of our machines? So this is a very simple program, just hello CUDA, that we have here. And what this program will do, it will run the command echo. Our application is just running echo on a GPU, and it will return the value of CUDA visible devices. So if you have a GPU enabled program that uses CUDA and relies on CUDA visible devices to pin work to GPUs, you could, for example, slot this into an app that looks very much like this, and you can see how you can run an instance of that application on, independent GPUs on a Polaris node using this example. So what are the different parts of a Parcel program? So the first thing is the config object. And so Parcel works by separating the program logic from the machine configuration. So this config object, and we'll talk about what that looks like in a minute, this is what contains all the information Parcel needs to communicate with the scheduler and distribute tasks over compute nodes. But that is done independently of the program, essentially. So once we load that config, Parcel should know how to do that, do those things, communicate with the scheduler and distribute tasks to compute nodes. The second thing is you need to create an app. So this app, as I said, just echoes the value of CUDA visible devices. And so if you run many instances of this app on, one per GPU on a Polaris node, it should give you a different value for CUDA visible devices. Then we create tasks that call the app, and we're going to create 4 tasks, 1 per GPU. A Polaris node has 4 GPUs. And what we will do is we will save those tasks to a list, a Python list called tasks. And once we invoke these apps, this creates the future, and this will sort of start the process by which Parcel will, starting this script will start a Parcel process. And once we create tasks, the process will start trying to fulfill those tasks, which is to say, it will start writing a batch script, it will submit that batch script to the scheduler, and it will start trying to run these tasks on the resources provisioned by the scheduler. And then this last piece here is a piece where we will wait for the results of these tasks to be returned. And we can create that waiting by invoking t.result. And so in the case of a bash app, a successful application will return a 0 if it's run successfully. So we will check to see if they have run successfully and then print the results as standard out. So how long will this script wait? So essentially, if you're running this at the command line, it will kind of appear that the script will hang. It's not hanging, like the process is doing things in the background. If you don't like that, you can, for example, put this script in the background using an ampersand when you call it, or you can use screen to run it in a separate process from your shell. So the time that it will wait will depend on the queuing time of the batch job that Parcel will start up, and then the execution time of the task. So sort of in summary, executing this script from a Polaris login node will start a process that will create these task futures, write a Polaris batch script, submit it, and then wait for the results. And this is a pretty small example, so all of the tasks should be completed. But if there are outstanding futures at the end of the batch job, Parcel will automatically spin up more batch jobs. And the output of the program is just shown here at the bottom, where it just prints, hello Polaris, CUDA device 0 through 3. So we sort of—
Kristen?
Yeah.
We have a couple of questions that I think we should probably answer before we move forward.
Yeah.
So the first question was about the in general, like what is the ensemble jobs, and and Chase was asking if it's similar to array jobs that schedulers like PBS or Slurm have that.
Right. Yeah. So yes. So yeah, PBS and Slurm. I'm less familiar with Slurm, but I know PBS has array jobs, and yeah, it's similar. This is something that we did with recommended to use with Cobalt, which was the scheduler on Theta. And so in the ensemble batch job, essentially what you do is you just create multiple well, on Theta, that would be app run commands. So you can have multiple commands within the same batch script, and you just add an ampersand at the end of each app run command, so that the application will be launched, and it will then continue to the next line and launch the next application. So it's just a way of launching multiple app run commands or MPI exec commands in the same script. So it's similar to, I think, the array jobs in PBS. Cobalt doesn't have array jobs, so that was sort of the way it was approached there, but it is very similar, yes.
Thank you. Next question was with respect to the Parcel, and it's asking, so Chris is asking, how do ALCF users use Parcel for managing multiple concurrent MPI tasks? I have not found a good way to do that, and I'm exploring using the Flux executor or Radical to handle that. Wondering if there is another alternative.
Yeah, so I would say that Parcel, running MPI tasks, especially multi-node MPI tests, is not well supported in Parcel. Parcel is very useful for high throughput workflows where you're running many tasks that run one per node or one per CPU or GPU. I think Radical might be a good choice. I'm going to talk about another tool called Balsam in a minute that is also very good for this. So if you want to wait and see if the Balsam portion of the talk might be useful to you, that could be a good choice. Yeah, there are ways of getting Parcel to run multi-node MPI tasks, but it is a bit awkward, and it's not really currently the best choice of tool for that type of workflow, I would say.
Thank you. I think, yeah, let's move on to the Balsam, so maybe that answers the question.
So I guess the last piece of Parcel was, I was just going to mention the config, because you saw here we were loading this config object. So you can run this script on any machine, but you will have to swap in the appropriate config object for your machine. This is an example of, and basically what the config object does is it just tells Parcel how to communicate with the scheduler and how to distribute what's called the manager, which is a process on every node that will manage workers. And each worker will run one app at a time, essentially. So this is an example config for Polaris, and I won't have time to go through all of the details of this, but there are extensive documentation on the Parcel website. But essentially, this example config will submit one node batch jobs to the debug queue on Polaris under my project named Data Science. You would have to put in your own. And these batch jobs will run for 10 minutes each. You are here using what's called the MPI exec launcher, and it's important and related to that question. This does not refer to how Parcel runs your application. It refers to the method by which it distributes the managers to the nodes. So this is a common misconception, but this sort of setup of using the high throughput executor with the MPI exec launcher is sort of a common and useful config to run on Polaris. This will put one manager on every node, and it will put one worker on every GPU. Okay. So I'll just also briefly mention Parcel is part of the Globus Labs, which has many other tools. They have a tool called FuncX, which has actually been rebranded. It's now, as of like last week, called Globus Compute, which is a way of distributing work remotely to machines. But it actually uses Parcel at the end point on the machine. And so the Parcel config you write to use on, Polaris will look very similar to the config you will use for Globus Compute, for example. So just a few concluding thoughts about what is Parcel good for. And as the questioner noted, it's maybe not great for multi-node MPI jobs, but it can be a good choice if you're running, a very high throughput workflow where you're running many tasks per second on single nodes or single CPUs, GPUs, or, there's many advantages, and they're listed here. One thing I'll point out, in contrast to the next tool I'll talk about, Balsam is very lightweight. It doesn't depend on any external database, for example, and there are many other tools that are database-based tools. And there is some overhead associated with working with a database, which if you don't need that for your workflow, that might be a consideration. And Parcel is sort of a lightweight alternative to those types of models. So I'll just highlight that and just note that you can go to the Parcel Slack and docs for more information. Okay, moving on. So the next tool we'll talk about is Balsam. So this is a tool that was developed at ALCF and is used for deploying workflows on DOE machines. So this runs on a database model. So applications and tasks are stored in a centralized database on a server that tracks the progress of tasks that we call jobs in the Balsam lingo. These jobs can execute external compiled applications or native Python apps. It has a Python API and a command line interface. You would install it based on sort of in a similar way to Parcel. You can install it in a Conda module shown here, or a Python virtual environment. One thing to note is that it works with this centralized server. And this has some advantages, but some other considerations to think about as well. having a centralized server means that you can deploy work for the same workflow on different machines, because the representation of your work, the apps and the jobs, exist in the cloud, essentially. But also having a centralized server requires you to have a login to that server. Currently, there's only one Balsam server. That might be changing soon, actually. But the one Balsam server that we have is hosted here at ALCF. So even if you're deploying work at NERSC or OLCF, you will need an ALCF account to log into the server. We have, in contrast to Parcel, we try to do as much configuration specific to the machine for the user. So there are supported configurations in Balsam for specific machines. And we'll show you in a second how you would set that up. So sort of the schematic of the model is that, you have a user on a laptop. They will create what's called a Balsam site, and we'll show you how to do that in a second. But basically, that's sort of the workspace for your workflow that exists, that has a representation on the file system on the machine, but also exists in the cloud on the ALCF server as well. The user will create applications and jobs in the Balsam site by either running Python scripts or through the command line interface. These applications and jobs are stored in a database. Then the user can create what's called a batch job object. And when this happens, the site, which will communicate with the scheduler to provision nodes to submit a job to the scheduler, which will provision nodes that the batch job object can then deploy jobs to. So the batch job will pull jobs from the database and then put them on the compute nodes that it has gotten from the scheduler. So this is the basic sort of schematic model of what's happening in Balsam. So I've alluded to the Balsam site. What is that and how do you set that up? So the first step to creating a workflow in Balsam is to make the Balsam site. The site is composed of two elements. It's a workspace directory on the machine file system that contains data, logs, and settings. And then it also has a background process that runs on the machine persistently and communicates with the machine scheduler and the database on the Balsam server. Sites are active when the background process is running and communicating with the server. The site needs to be active for the workflow to work, essentially. And then the sites are configured for the machine where they are locally set up automatically for the user. So shown on the right here is just an example of what you would do on the command line on Polaris to set up a site. So first you would, install Balsam, as we showed in the previous slide, and then you would have to log into the server. You do that by typing Balsam login. It will give you a URL that you will then paste into a browser, which will direct you to a place where you will put in your ALCF credentials. So your username and your mobile password. Then you will create a site by typing Balsam site init-n. This is the name of the site. And then this is the path to the site, which I just gave it the same as the name in this case. When you type that, you are presented with a menu of possible machines where you can create a site. And so if you're on Polaris, you will just scroll down and select Polaris ALCF, but you can see here we have configurations for Summit at OLCF, for Perlmutter, both with the CPUs and the GPUs at NERSC, and all of our other ALCF machines. Then you will have to go to the site directory, so CD to that. So running this will create a directory on the file system called Polaris tutorial. You'll go there, and then you have to run Balsam site start. So that will activate this background process. And you can query whether that site process is active by typing Balsam site ls. And if it is active, it should show you some output like this, that it's active. Yes. So how do you then, once you've created a site, how do you run work on the machine? So this is just a very simple example running a compiled executable called LAMPS. This is a molecular dynamics code. The executable is called LMP. Not important, but basically it's an executable. It can take some input values. That's all you really need to know. So this simple example, the Balsam script contains 3 parts. First, you have to create an application. Then you create jobs that run the application. And then you create a batch job object, which is the point at which the Balsam site process will communicate with the scheduler and submit a batch script to the scheduler. So first, to create the application, you will create a Python class called LAMPS. That's of type application definition. This is part of the Balsam schema. And part of the application, you have to define the site that it's attached to, and you have to give it the executable, which is contained here in this this variable command template. So this is basically the string that will execute your application. In this case, it's the executable, and then like an input file. And then here we're passing it a variable, a parameter, and you can denote that by wrapping it in these double curly brace brackets. You might also want to, for example, load some modules or set some environment variables or add this executable LMP to your path. You could do this through something called the shell preamble. This is a piece of command line commands that will run on the compute node just prior to your application defined in the command template, right before that runs. So here I just source a shell script that will contain everything I need to run LAMPS, for example. Then you have to run this lamps.sync. What this does is it saves this application definition to the database on the server. This is very important. You won't be able to run this application unless you save it to the database. Okay, once you've done that, you can create some jobs running LAMPS in this way. So we're going to create 3 jobs, one for a different value of the parameter. And we can do this in a simple loop, and we'll save them to a Python list. And once you create these jobs, they have to have the parameter. Any required parameters have to be specified here. Oh. And then you have to give it a work directory, which is a directory within your site where the outputs of the application will be written. Once you create these jobs, you have to then, again, save them to the database. You can do that with this call here, this job objects bulk create. This will save them to the server, give them a job ID that you can then track them in the database with that ID. So once you've created your application and your jobs, you can then spin up what's called a batch job. You'll create a batch job object. And as part of this object, you have to tell it things about your project name, the queue you're running on, the wall time limit. This job mode MPI, what this means is that when you run something in job mode MPI in Balsam, it means that whatever command you give to command template, it will be passed to the MPI executor on that machine. On Polaris, that would be MPI exec. On Theta, that would be AP run. And essentially what Balsam will do is it will construct an MPI exec call for the application using what you tell it about the job resources that it needs and the application call, essentially the executable that you define. So how do you define those resources? So I didn't really give a long complex example in that previous slide, but here, if you wanted to sort of specify for each job shown in this code snippet here, you can define how many nodes you want it to run on, how many ranks per node, all of the things you would specify on like the MPI exec line to run the application. How many ranks per node, GPUs per rank, threads per rank, any additional launch parameters that need to be passed to the MPI exec line. You would define that within the job instance that you create. And one important thing to realize is, you can run the same application, say lamps, multiple times, and you can change the resources and the run settings, and you can make those different for every single job. So you could run a bunch of 1 node lamps jobs, a bunch of 2 node lamps jobs, 4 node, 8 node, and you can save them all to your site. And when you create a batch job, Balsam has a model for asynchronously packing jobs into the nodes available in the batch job. And so this is just showing you a little example of what that would look like for sort of just a 3-node batch job. Suppose you've got, a couple of jobs, some need 1 node, some need 2 nodes, they run for different amounts of time. And what Balsam will do is it will pull from the database, and if this is nodes and this is time, it will start out running these 1 node batch jobs, and those may be run very quickly, they complete, and then it will, as nodes free up, start filling in batch jobs that are available to run. So then maybe we'll start a 1 node and a 2 node batch job. When this 2 node one finishes, maybe it starts a new 2 node job, et cetera, et cetera. It's important to note there could be points of time in this batch job where there might be some idle time for some of these nodes. So it's important to think carefully about how you select jobs to run in a batch job, and there are ways you can control that in Balsam. You can get more information on sort of defining compute resources for jobs at the link here in the Balsam docs. So why choose Balsam? So Balsam is an excellent choice if you need to run a large collection of multi-node MPI jobs. So this is something that, for example, Parcel is not is not well supported for some tools. Balsam can, like Parcel, handle job dependencies. I didn't show an example of that, but that is also possible. Balsam runs on a database model, which means that there is a record in a database for every single job that is run or task that Balsam runs, tracking how long it took, all the details about how it ran. For some workflows, like that's an important need and people really want that. For some workflows, like the overhead associated with having the database isn't really worth it. Like some workflows, they may not want or need that information, but Balsam has that available. Again, I think I mentioned before, the database is hosted in the cloud, which means that you can deploy jobs to different machines from within the same workflow. You can create basically job dependencies between jobs running on different machines, for example. You could start a simulation on Perlmutter, and when that completes, maybe start an ML model on Polaris. Like that is like a possible thing to do. Balsam has support for data transfers via Globus Online. I didn't sort of go into it, but I showed you examples of sort of the static batch job scheduling that the user controls explicitly, but there is also an elastic mode where the user just gives the site some limits and it will just automatically spin up batch jobs when it sees that it has available work in the database, similar to sort of what Parcel does by default. So you can get more information about Balsam on the Balsam documentation page. There's also a Balsam Slack that you can join if you would like to get help there as well. So yeah, so where to get more information? Parcel has extensive documentation. You can also access their GitHub if you want to look into their code. They also have a Slack that is very active. I know because I'm on it, where people, where the developers there are very helpful to users trying to figure out things. I guess I'll also point you to the website for FunkX, which maybe is changing because it's been renamed to Globus Compute, but that allows you to sort of deploy Parcel workflows sort of remotely from the cloud, essentially. For Balsam, there's documentation here. You can also see our GitHub and join the Slack. One thing I will mention is about 2 weeks ago, we had a workflows workshop jointly between ALCF, OLCF, and NERSC, where we did tutorials on a bunch of different tools, including Parcel and Balsam, but also GNU Parallel and Fireworks. And we have a repository here that with this link that gives you examples for running all 4 of these tools at all of the different DOE facilities, including ALCF. So there's if you want to see an example of how to run Fireworks on Polaris, there's an example you can find in that repo, along with Parcel and Balsam and GNU Parallel. And I guess I'll just also mention that there's a whole workflows community that develop software for workflows. And, you know, if you're sort of interested in exploring other tools that I haven't talked about here or discovering other tools, they have some resources they have some really great resources on their website. So just in summary, what we covered here today in this webinar is how to deploy large job campaigns on our machines. We talked about the things you need to think about when you have a large collection of jobs. And we talked about the 2 tools that we commonly use here at the facility, Parcel and Balsam, to accomplish this. We talked about tools that are well suited to run high throughput workflows of small single node tasks, but also tools that can run large numbers of multi-node MPI jobs. There are, of course, many other tools, and there are also this whole suite of sort of the higher level tools that will tell, you know, workflow tools what jobs to run through hyperparameter space inference or hyperparameter space searches or machine learning inference. We didn't cover that today, but those tools do exist. And I guess like it's just important to point out, like, machines are only getting bigger. There's going to be even more need to run and support workflow tools. And if you're not currently using a tool, I encourage you to explore whether a tool might be right for you, because yeah, machines are getting bigger. You should be thinking about what you need to do to scale up your workloads to larger machines and what kind of questions you could answer if you could run on larger machines. And because the space of tools to support that does exist, and we can help you to do that. So with that, I'll just conclude here and take any additional questions. Thank you.